Okay, so let's set this up for all of the geometries that we will need. We are going to do this only for steric numbers 2 through 4. So you will not have to deal with steric number 5 and 6, just 2 through 4. So just to restate it before we go in, valence bond theory produces a picture consistent with VSEPR. So you should be able to, and it will help you to, look at a molecule, determine the VSEPR geometry around the central atom or the atom that you're looking at, and then pick out what the geometry should be like to know where your orbitals are going to point after you hybridize them. So starting with steric number 2, we need to make bonds 180 degrees apart. If I gave you something with a steric number of 2, you would be able to tell me that the base geometry is linear, and so that's how we make a linear molecule. The way that we do this is that we will take 2 atomic orbitals on beryllium and combine them. So for valence bond theory, you will pick an atom, count the number of things around it, determine its geometry, make hybrid orbitals that point in those directions, and then overlap them with adjacent atoms' orbitals, hybrid or regular, in order to make the bonds. So what this looks like, in beryllium, the valence orbitals are 2s and 2p. So I'm going to take the 2s and one of the 2p orbitals and smash them together and make sp hybrids. So right, I have this written with no space, sp hybrids. So right on the left, I have what the energies are to start out. On the right, what this would mean energetically after we hybridize them is that I have sp hybrids. I have 2 of them. I also have the number 2 out front because n is equal to 2. We're going to start leaving off that front number for this reason. Those 2 at the same energy, and then my p orbitals that were unhybridized, we didn't do anything to them, they're just left over, are at the energy that they were at before. You will not need to recreate these energy diagrams, but this is like what we mean by we're mathematically combining them. Now you will need the picture version. So the picture version of 2 ways to add an s and a p orbital together, that results in the 2 hybrids. I could take my s orbital and my p orbital such that there's destructive interference on the left side and constructive interference on the right side. So what I have in this picture, I've got my p orbital, I've set my s orbital on top of it because they both center at the nucleus of the atom, and I have added them mathematically. So if my s orbital is unshaded, then the side of the p orbital that is unshaded will constructively interfere because they're in the same phase. Constructive interference for drawing this hybrid orbital means it's bigger on that side. On the left side, I've got shaded and unshaded. That's a destructive. The lobe on that side is going to get smaller. Now, the other way that I could add this together is if my p orbital were shaded the other way, and this gives me constructive interference on the left, destructive interference on the right. So my 2 pictures here, each one is an sp hybrid, and we will be using these to make the bonds. Okay, the way that we use these to make the bonds, on the left, this hybrid orbital is centered on beryllium, and with the way that I have this structured based on our normal axis system, the p orbital that I'm using is the px orbital. My hybrid is pointing to the right. The big lobe is what's going to do the constructive interference to make the bond. So I've got my hydrogen 1s overlapping with it. For the other hybrid orbital, it points in the other direction. So it is going to overlap with the hydrogen 1s orbital that's on the other side. So the way that I have these labeled, I have a beryllium sp hydrogen 1s sigma bond. It is a head-on overlap. It's a single bond that is also a sigma bond. It was made from an sp hybrid on beryllium and a 1s on hydrogen. Same on the right side. This, with the stars around it, this is how you will be asked to draw the pictures. This is how I would like you to draw the pictures and label the pictures. Below it, I do have a full picture because I don't want you to forget that these are happening on the same atom, right? They're all centered around the same central atom. We're providing the geometry around beryllium. So if I were to put this all in one full picture, my beryllium, in the black ink, I have the large lobe of my 1 hybrid orbital that overlaps with hydrogen 1s on the left. In blue, I've got my big lobe of the sp hybrid on beryllium overlapping with the hydrogen 1s. Right, you can see that it gives you 180-degree bond angles. But also, because all of these orbitals center on beryllium, it's really hard to show the full orbital. So we will not draw this full picture. Please don't draw this full picture. But I wanted to just remind you that this exists, that this is what exists. Okay, we'll come back for the leftover p orbitals in a little bit. Let's set up steric number 3. So steric number 3, we know that's trigonal planar. We need bonds that are 120 degrees apart, all in one plane. BH3 will let us do a great example of this. So my Lewis structure, and actually also my VSEPR geometry, looks like this. Boron in the middle, hydrogens attached, 120-degree bond angles. It only had 6 electrons, but boron is very happy with that. There are no formal charges. So steric number 3, I will combine 3 of the orbitals on boron to make hybrids. So that's the s orbital and 2 of the p's. So we call these sp2 hybrids. So with my axis system, I'm going to use px and py because they are all in one plane. They'll be all in the xy plane. And my molecule is all in the xy plane. So I can't have orbitals pointing where my molecule is not. Molecule in the plane of xy, use px and use py to make the hybrids. The result here, which I'm not going to do the individual drawings like I did for sp, but if you take 3 orbitals and combine them mathematically, this is the result. So if I were to use these, I end up with a big lobe pointing in the direction of one of my boron hydrogen bonds, and then like straight up, then down to the left, 120 degrees away, that's where the other big lobe points, and 120 degrees from that down to the right, that is the other lobe of the hybrid orbital that results. So combine 3 orbitals, an s and 2 p's, you get these 3 sp2 hybrid orbitals out of that mathematical operation. So if I use these to draw pictures of the sigma bonds in BH3, I have a boron sp2 overlapping with a hydrogen 1s sigma bond. And maybe a little bit of good news, this boron hydrogen bond, the other 2 pictures would look identical. So still a boron sp2, still the hydrogen 1s, right, resulting from that hybridization we did. I can just say plus 2 more. You'll need to draw one example of each type of bond. Now, just beware for cases when the bonds might kind of look the same, but were made from different orbitals. We'll see those more complicated examples as we go. All right, steric number 4, we need 4 bonds. We need them to be 109.5 degrees apart. And I mean, let's just continue our trend of only having hydrogens connected and do CH4. So steric number 4, make 4 bonds, put in 4 orbitals. Well, that's my s and all 3 of my p orbitals. So I'm making sp3 hybrid orbitals. When you mathematically add these all together, the result is hybrid orbitals that point exactly 109.5 degrees away from each other in a tetrahedral geometry. So for CH4, if I were to write this sigma bond, I'm drawing a carbon sp3, hydrogen 1s sigma bond. Now, the other three bonds would be identical, so I would only need to draw one example of this. But take a look. We determine the geometry based on the steric number. That also determines the hybridization, because our resulting hybrid orbitals from whatever mathematical smashing pictures together that we need to do will point at the angles that we need them for the specific geometry. Don't stress, we will do a bunch of examples. Let's talk about what happens to these leftover orbitals first. So sp3, well, if I use my s and 3 p orbitals, there's nothing left over. So in sp3, we are putting in all 4 available orbitals that are in the valence shell. The hybrids that come out, I mean, we get 4, there's nothing left over. For the sp2s, well, if we use the s and 2 of the p's, I have a p orbital that's left over. I did not hybridize it. And in sp, I only used one of my p orbitals, so I have 2 p orbitals left over. So one question is, which p orbital is left over? And kind of hinted at this with putting together the structure of BH3. So, I mean, let's look at it a little more explicitly. So we said, or I said, I was going to use the px and the py because my molecule was in the xy plane. Now, you can choose how your molecule is drawn. This is probably how most people would choose to draw it. So I have my molecule in the xy plane. So the bonds that I'm making have to be in that plane so they can point in the right direction to make the bonds. It's the pz orbital that's left over. So in BH3, what that looks like, I've got this on the bottom with my molecule in the exact same orientation. Molecule in the xy plane, pz orbital here in orange, just coming out and going back in the paper. If I rotate this, so I've done this by like rotating my entire axis system so that it is still the pz orbital that's left over, I have my molecule in the xy plane with how my axis system has been rotated. What that means is that I have a hydrogen coming out at me and a hydrogen going back, and then one in the plane along the y-axis. And then my pz orbital, it's centered on boron, which is why there's one lobe above and one lobe below. So that's, I mean, it's not going to seem terribly interesting right now, but it's super important for the mechanisms that you'll do in organic chemistry. However, you can maybe see what other options we have for using these p orbitals as we do some examples. Now, before I do the example, we should look at sp. So our BeH2 was the example molecule that we had that was sp hybridized on beryllium. The molecule, the way that it's drawn is just like along the x-axis, and that's pretty much it. For linear molecules, it's aligned with the x-axis. Then we could align it other ways, right? That's something that we can try in class. But if we do this, it means we have to use the px in the hybrid so that the molecule points, the bonds that the molecule is making are pointing in the right direction. And what that leaves us with is a py and a pz that were not hybridized, that are just left over on beryllium. And so that's what I have drawn, just a regular p orbital on beryllium. One of them is px and the other one is pz.